forgotten. Sorry, I forgot to turn on the recording. So here's a quick review. They've been impressing me with their vast knowledge of science. Okay. And so work, we have defined work to be force times distance. And if you're in the metric units, you can take your forces in newtons, your distances in meters, which means you get a newton meter. But instead of calling them newton meters, we can also call them joules. Okay, when we're in English Standard, though, do I change the, we just call it foot-pounds, which personally has always bugged me as one of the most strange units. Okay. All right, there you go. Use foot-pounds all the time in auto class. So, okay, now, here's the difference in what you've done in science class versus what we're going to do in calculus. In science class, I might have told you that I applied a force of 20 pounds, and I applied that force for a distance of 10 feet, and you guys would tell me the amount of work I did is what? Is 200, because you would take 20 times 10, and you would get 200 foot-pounds. Okay. That assumes that your 20 pounds of force was constant. The entire time you were moving it, you were putting an equal force of 20 pounds the entire way. That assumes force is constant. Well, with calculus, we don't have to have constant forces. We can have our force vary. I think that makes it harder. So when our force varies, our force is going to be some function. And so if I, for example, here give you a basic, I could be applying maybe for the first 3 feet, I could apply a force of 10 pounds. And then for the next 2 feet, my force has dropped to 8 pounds. And then for the next 2 feet, it drops down to 6 pounds. My force is varying. If I can come up with a function to represent how that force is changing, I can still find the amount of work done. In our case, though, they're not going to break it down in units like that. They're just going to say, okay, I actually had some change in the distance here. What do we use to represent change in? So change in the distance times whatever this first force was. Then I'm going to have a different change in the distance times the next force, etc. I still need to take force times distance. So we're going to come up with some function to represent force, which is this capital F for force, f of x, not normal little f of x, but capital F for force. Okay, what do we usually use when we're doing our integration problems to represent the change in something? Delta x becomes dx, the change in the distance. So so dx actually represents our change in the distance. And if I want to sum up all these different little segments, what can I do to make it sum them all up? The sigma thing. And then I put a limit on it to make my distances all go towards 0. Yeah, so in other words, it means it becomes what? It becomes integration. It's nothing more than the integration of the force times dx. From A to B being where you move it from here to here. So the formula itself, not a bit complicated. That's work. So technically that's the formula for these problems. You're really not even going to ever refer back to that formula. You're just going to have to come up with a way to express force. Okay, so, yeah, I can. Okay, all right. So, now we'll attempt to draw here. This is the ground. This is a well in the ground. Right? And above the well, we have your little well thingy with the crank and the handle and the rope coming down with a bucket on it. Think Jack and Jill, who went to get up the hill to get the pail of water. So, all right. In this case, our well is 40 feet deep, and that 40 feet actually is the distance from where the well, we make it to the top of the well here, down to the height of the water. So that's 40, it's 40 feet. We've got to lift our bucket, essentially. And the big thing is, I'm going to tell you that the bucket weighs 30 pounds when it's full. However, there's a hole in our bucket. You guys actually know that song?
Oh, am I the... I don't know.
Wow, I'm impressed.
I just like to look at it. Probably right up there.
Yes, it gets annoying. I learned it singing it in elementary music.
Well, from a different song.
Okay. So the water is falling out of it. As we raise it up, we're losing water. So in this case, we're losing a quarter pound for each foot we raise it. The question is, how much work does it take to get this thing lifted to the top? Now, using our incredibly helpful formula, which says it's just how the force is changing times dx, that's not giving us a whole lot to work with. Okay, we need to go back to physics. Basic general science type style physics. How much force does it require? If I was lifting this bucket above my head, how much force does it require for me to lift it straight up above my head if it's a 30-pound bucket? 30 pounds force. Where its weight is how much gravity's pulling on it down with 30 pounds force, so I've got to actually push with 30 pounds more to get it smooth. So the weight is your force. But is that weight staying constant? No. So what we actually have to do is we have to come up with, okay, I'm starting with 30-pound bucket. Okay, Megan's guess is 30 minus 1/4 x, with x representing what? Yeah. Well, how many feet you are? So you're starting at 30 pounds, you're losing a fourth a pound for every x feet. Okay, seems very logical. And then, okay, Haley says from 0 to 40. She would be right. Ta-da! Yes, you're going to put in your calculator and get an answer. Which I can actually tell you the answer. That works. It comes out an amazingly nice round 1,000. 1,000 watts. Well, we must. We're in feet pounds, so we are foot pounds. So it's going to take 1,000 foot-pounds of work to move this thing. Foot times pound, that's divided by. There's an actual dot in there. Okay. Now my problem is I've never worked with foot-pounds, so I don't have a concept of, is 1,000 foot-pounds a lot or little? Okay, yeah. Okay. Because how tight you have a lug nut on a wheel and how much pounds. It's a fair amount of work, it's not a whole amount of work. Now, here in a few minutes, after we do a couple more of these, calculate this, and you guys have a problem on your assignment then that tells you that a so many horsepower engine can do this much work. So then you can figure out how much horsepower you need to do one of the pulses of it. So there's the well. Another one. This time we have a crane. The crane raises the bucket of sand. Okay, when I say a bucket of sand and I'm talking about a crane, am I talking about a handheld bucket? I'm talking like a big on your project here. Okay, so crane raises bucket of sand weighs 500 pounds. With a bucket, from the ground, a height of 50 feet. I am. It does that. It raises it to 50 feet in 10 seconds. I threw a time element in this. Okay, however, yeah, they've scooped this big, you got the sand, and the sand is, it's falling off over the edge. It's not like they haven't let it out. Some of the sand is falling out as it is pulled up, and it's filling out at the rate of 10 pounds per second. The other thing is, if you're lifting something this heavy, the cable that's attached to the framing isn't going to be just some little rope that weighs nothing. The cable is going to be pretty substantial too, and it's got to weigh. So in this case, the cable weighs 5 pounds per foot. How much work is needed to raise it to a height of 13.5 feet? So why has this one got a little more pizzazz to it? So I really don't need a whole much of a picture here, but if you really, this is trash. You got your basic frame, you got your cable, you got your bucket of sand, and you got all the sand parts. So, the two parts you have to worry about on this problem. What are the two parts? Yeah, you got to worry about sand in the bucket, and then you got to worry about the cable. You actually got two different things happening here. You have to have something represented on the force each. So which one do you want to do first? Sand? Okay. So, I always work from what am I starting out with as far as the sand? 500 pounds. You know you got 500 pounds starting with, but is it going up or down? You want your sand out, so it's going down. The question is at what rate? So you have to know how to change things because we're integrating based on feet. So we have to know how much are we losing per foot. I'm losing 10 pounds per second. How do I get 10 pounds per foot in there? You can common sense this, or you can use the good old unit calculation that we've been using up here forever. I need to get rid of seconds. I want to get rid of seconds, and I need to get them into feet. So what do I know? I did 50 in 10 seconds. How by 50 value 2 pounds per foot that we're using. So, if you're ever in doubt about conversion, use the conversion rule. It'll do it for you every time. Oh, booger. Yes.